whenever you lift something up, you're doing work against gravity. Okay, so when I make that statement, I know to you guys it means absolutely nothing, despite the fact that that's just about the most important stuff that I'm talking about during the past 20, 25 minutes. All right, so by lifting something up, you're doing work against gravity. All right, so that's the acceleration due to gravity by lifting something up. So which means that the amount of work that I do in lifting something up is going to go into the potential energy of the subject. All right, so which means that this energy is going to become stored in the subject. This is known as a gravitational potential energy. Now, gravitational potential energy is going to depend on the location of the subject, or as you guys were talking about in physics 1, it's going to be the height. So higher up you go, the more potential energy object is going to have, which means that the more energy is going to be stored in. All right, so that's your potential energy constant. So PE is your potential energy. All right, so I usually use PE for that. All right, and some books use V, and some books will use U. And then when you get up to the graduate level, all right, so this is going to become 3 or 5. Okay, so you'll see different symbols. In my notes, I end up using U because that's the same symbol. Some books use V. Okay, so that's the same thing. All right, so the next concept is the kinetic energy. So the kinetic energy is the energy of motion. All right, so it's going to be related to speed. All right, once again, it's a straightforward concept speeding up in this direction. So my question to you is, given the fact that the car is speeding up, is there any work being done on this car? All right, so, okay, your speaker is not working. I don't care. All right, so what is the amount of work being done on the car? Any ideas? How much work is being done on the car? Is there any work being done on the car? All right, here, yeah, go ahead. Okay, now
I was just saying yes, there is.
Okay, so Caleb, you're saying work is being done on the car. How did you arrive at that conclusion?
Because there's a force, and you can see this accelerating and acceleration.
Okay, I'll give you 10 points. Beautiful. It's accelerating, guys. What causes the acceleration? A force. And notice that the force and acceleration will be in the same direction, and notice that the displacement is in the same direction. So the work is being done in this car, except the amount of work that you do on this car is the amount of energy that gets transferred is going to appear in the form of motion. So that's known as the kinetic energy. And energy motion is going to be related to speed. So that's the second thing that we need to go back and clarify. We're not clarifying, more like reviewing. All right, so the second sort of energy that we deal with is the energy of motion. So it's going to be related to speed. So this thing is moving, it's got mass. All right, and because it's moving and because it's got mass, it's going to have speed. It's got mass, obviously, square the speed, everything divided by 2. I use the letters KE. So this is your kinetic energy. All right, once again, depending upon the books, I mean, you can use K, that's another one, and at the graduate level, you can end up using K, so that's the same thing. All right, so different symbols, same concept. So kinetic energy is the energy of motion, and kinetic energy depends on the speed. Potential energy depends on your location or height. And then the next concept is the mechanical energy. All right, so what is mechanical energy? Mechanical energy is a combination of kinetic and potential energies. All right, so it's a combination. It's the sum of kinetic and potential energies. That's the same as total energy in this case. All right, mechanical energy is the combination of kinetic and potential energies. Conservation of mechanical energy is the next question that we need to answer. Conservation means the constancy. So which means that the mechanical energy is constant. When somebody says mechanical energy is conserved, which means that the mechanical energy remains constant. So that's the constancy of mechanical energy. All right, so mechanical, so which means that the total energy, so when you sum them up, it's going to remain constant. All right, so it's going to remain constant if that's the case. So we don't get this. All right, so here's the next question. If I drop something, all right, so if I drop this, what happens to potential energy? Notice that potential energy is going to go down. What happens to this kinetic energy? Kinetic energy is going to go up. Okay. What happens to this mechanical energy? If mechanical energy is constant whenever you drop something, what happens is the potential energy gets converted into kinetic energy. Only if this is constant. Got it? If the mechanical energy is constant, the potential energy gets converted into kinetic energy. All right, so if you throw something up against gravity, as the potential energy goes up, the kinetic energy goes down. What that means, the kinetic energy gets converted into potential energy if the mechanical energy is constant. Okay, so here's the dumbass question. It's a dumbass question because the answer is kind of weird. What conserves mechanical energy? All right, does anybody know? What conserves mechanical energy? Under only very special circumstances, you can assume that the mechanical energy is constant, guys. What are those circumstances? You cannot.
No air resistance, and the only thing acting on it is gravity.
Okay, who said that?
Matthew.
Okay, Matthew, I'm going to give you 5 points. Mechanical energy is going to be constant only if there's a conservative force acting on something. The force has to be conservative. Just remember that. This is a bit of a mathematical definition. In order to make it work, only conservative forces can conserve mechanical energy. Gravity is a conservative force. So this thing is constant because gravity is a conservative force. All right? Just remember that, because gravity is a conservative force, which means that all right, gravity is a conservative force. All right, so which means that you have to ignore the non-conservative forces like air friction or propulsion or whatever because of gravity. So this is going to be constant. Okay, have you seen, obviously in physics 1, you guys have seen gravity. Your instructor, I'm sure, talked about gravity being a conservative force. If he didn't talk about it, more than likely he mumbled it for a while to himself. All right, that's the way you guys usually perceive that. What's another conservative force that you guys have seen? The second conservative force that you guys have seen was, remember the last
Spring force.
What is it?
Spring force.
Spring force. You guys have 5 points. Absolutely, guys. The restoring force is a conservative force. Absolutely, yeah. So which means that the mechanical energy is conserved. So by definition, any force that conserves mechanical energy is a conservative force. Gravity is a conservative force. By lifting something up, guys, what am I doing? I'm doing work against gravity. So every time you do work against the conservative force, you're able to store energy in the object that you're moving against the conservative force. It's called potential energy because this potential energy is the amount of energy that could potentially turn into kinetic energy when a conservative force takes over. So it's got potential energy because I've done some work on it, right? As soon as I release it, what's the force acting on? It's gravity. So gravity is a conservative force. So what does it do? It takes the potential energy, the energy which is stored in it, immediately it converts it into kinetic energy. So the potential energy is the amount of energy that you store in something by doing work against the conservative force field, which means that the energy is stored, and the amount of energy that you store when the conservative force field takes over is going to immediately get converted into kinetic energy. So it turns into speed. That height is going to turn back into speed. That's a really, really, really powerful concept. So what do we know? When the only force acting on the object is the gravitational force, then the total mechanical energy is said to be constant, right? Because gravity is a competitive force. So which means that the total mechanical energy is going to remain constant. So the total mechanical energy here is all potential, and the total mechanical energy here all kinetic, right? So all that potential energy is going to turn into kinetic energy. So how fast something is going to be moving is only going to be the height. Case in point, this guy has what kind of energy? He's got only potential energy with respect to the bottom of this mountain or wherever he is. So
Take the end of the tape measure and then they flip a coin.
now when you trip, what happens? Gravity takes over, right? So what does gravity do? It's a conservative force field. So what does gravity do? This is called the conservation of matter. I love this guy's response reaction. What else is he going to do? Guys, you got two options. Either enjoy the scene or it's beautiful, or focus on some of that. So I think there's nothing much you could do on this circumstance. So mechanical energy is conserved. Notice that ignoring friction, gravity is the only force, so there's no change in mechanical energy. As the potential energy diminishes, the kinetic energy is going to increase by the same amount. That's what it means. So if there's a all right. So would they be moving faster or slower about the same speed if they were to jump directly into water down below, into the water down below? All right. The interesting thing is, if you ignore air friction, all right. So these guys are doing a pendulum move. So here's the top of the bridge, and all right. So I'm going to pivot this, and this is the cable that they're on. This is about 200 feet. So these guys are doing a pendulum move, and then the cable snaps or something snaps, and then next thing you know, there's going to be a splashdown. All right. Here's the initial height. Everything is up to the bridge. This is going to be 270 feet. And these guys are going like at 78 miles per hour at this point. And then I said when they hit the water, they're going to hit the water at 91 miles per hour. I've done the calculations before. All right. So question is, what would happen if these people were to jump directly into water? So let me just change color here. So imagine that these guys are just jumping directly into water. What do you think is going to happen? Straightforward. Guys, in both cases, ignoring friction, the only force acting is gravity. All right. So here's their initial mechanical energy. It's going to be all potential. Here's their final mechanical energy. It's going to be all kinetic. All right. If they're moving at 91 miles per hour, they're still going to move at 91 miles per hour here. All right. Path of motion doesn't matter. That's the nice thing about conservative forces. Path of motion does not matter. This is the reason why we love conservative forces in physics as well as engineering. All right, the only difference is this one is going to take a little bit longer. This is going to take a little bit shorter. End results will be the same. So gravity is going to do the same amount of work on both of them. All right, this one is going to take a little bit longer. So if you want to do sightseeing, this is the way to go. If you're in a hurry, this is the way to go. End result is still going to be the same. All right, so a lot of you guys usually focus on, hey, but what about the cable, man? You know, the cable is applying a force on it, so gravity is not the only force. I got news for you guys. The tension is in this direction. The motion is in this direction. This tension is not transferring any energy to the motion, or it's not taking anything away from it. Got it? So it's all gravity under the circumstances. So the path of motion does not matter. All right, in either way, if the worst case scenario, the first one is survival, it's also going to be survival in the second scenario. Direction. All right, so which ball is going to be moving at a larger speed? The largest speed. All right, which one is going to have the largest speed on impact? The first one, the second one, or the third one, or all of them the same? What do you guys think?
Does every ball have the same mass?
All right, yeah, and all three cases, they all have the same mass. It's the same ball projected at 3 different angles, obviously. So which ball is going to be moving the fastest? The first one, the second one, or the third one, or all of them the same? All right, guys, what's the best answer?
They're all the same.
They're all the same. Why is it that all of them are the same? They're all the same because they have the same initial mechanical energy, right? They have the same kinetic energy as well as they have the same potential energy. And right at the moment of impact, potential energy is 0, so it's going to be all kinetic. So all of them are moving at the same speed. So the path of motion does not matter. All right, the only thing that matters is the initial and the final point.